Welcome to the Gardien Podcast Series. The Gardien Group, providing extraordinary solutions to today's exceptional problems.
Hello, wherever you may be. Todd Kelvin again with the Gardien Group on another one of our podcasts in the series. Today, episode 11, what we're going to do is talk about four-wire Kelvin testing or high-resolution resistance measuring. I'm joined today, as usual, by Rick Moran out of Toronto, Canada. Glad to have you aboard, Rick. Hope things are going well.
Yeah, things are nice and sunny up here in Canada for a change, Todd. So it's a very nice, warm summer day. Thank you for asking. And I'm excited to talk about this topic here today. Four-wire Kelvin.
Yeah, it's if any of the people following us over the past, we've talked about four-wire Kelvin in the past, and it seems to be quite the newer activity. And so what we're going to do is talk about that today, give you some knowledge of where it came from, how it's used today. And I'll start out with a little bit of background. Kelvin testing, or high resolution resistive testing, or sometimes called Kelvin sensing, was invented by a guy named William Thomson. He was born in 1824 in Belfast, Ireland. When he was about 30 some years old, 37-ish or so, he came up with the Kelvin bridge, or the idea of high resolution testing. So back in the day, and still today, the standard 2-wire or ohmmeter you buy off the shelf, you can actually make measurements, but they only go to a certain resolution. And so Mr. Thomson, who later became known as Lord Kelvin, came with the idea where he could sense very minute changes in resistive measurements. And today, if we knew back then what we know today, this was a major advancement, because if we think about the other formula that we do all the time is Ohm's law. That's voltage equals current times resistance. Any minor change in resistance will affect current flow. And as today's designs are, when we're looking at really high-speed technology and timing circuits and things like that, when you have very small, minute changes in a resistive value, you can affect the current flow. And if you're looking very small traces or very small ICs that are very current sensitive, can have a major effect on the design or the functionality of the board. So this guy, way back in 1861, I think it was, that came up with this idea, had no idea in the future what would happen. He also was the guy that came up with the Kelvin scale for temperature measurements. Some of you might know that as the absolute zero Kelvin scale, or absolute zero, where molecular activity actually stops. He also came up with the term the joule, and that was also known as the Thomson effect. And he also came up with the kinetic energy phrase. But for today, we're going to be talking about the Kelvin bridge and, Kelvin sensing. So back in about 1861, he was doing some experiments where he was trying to measure small changes of resistive value, and couldn't get the measurement to work or find a means of making it accurate. So he came up with this term, the Kelvin bridge, where electrically, yeah, that's good enough, I guess, where he would actually take the measurement with 2 pins or 2 probes, and then he would actually use another set of probes where he could actually remove stray resistance, or the term came up called parasitic resistance, which is basically resistive value of your circuit that is caused by the meter, by the probes, by the wires. And that, using the Kelvin bridge theory, what takes out that parasitic or extra resistance, so you actually are left with what we call the true or pure resistive value of what you're measuring. So that's a little bit of background about Kelvin bridge and William Thomson. And we have to remember, when we talk about high resolution measurements, a lot of the industry started out with, checking plating quality or barrel integrity and things like that, of copper thickness. But as time has gone on, we have really high-speed circuits where we're dealing with satellite imagery, we're dealing with high-speed medical devices, aerospace, things like that, where we're actually really interested in the resistive value of the circuit itself and small changes in that value can also affect how the circuit functions, or, in this case, the final design. So that's a little background with that. Might have got a little wordy about it, but what we need to talk about next is our one wire versus, or two wires versus four wire, how we get into the Kelvin measurement. And I'm going to let Rick walk us down memory lane with that. Go ahead, Rick.
Todd, you gave us a lot of knowledge there. It's always interesting hearing it from you. I know that it's a little wordy, but it's the background knowledge everyone needs. It's theoretical. I know if you went to university, I'm sure you would understand all those parts for electrical engineering. You would fully understand four-wire Kelvin, two-wire Kelvin, but not all of us went down that route. Some of us are different levels of education. So a two-wire is, well, as it states, it's two wires. Normally, if you have a digital voltmeter, you're going to have a black lead or a common lead, and then a red lead, which is the positive. If you were to measure the voltage on anything, you need two leads in order to measure the voltage, but the same goes for resistance. You need to have a connection loop around it with current flow. So if you're using a digital voltmeter, the actually current flow comes from the positive lead of the meter around to the negative lead of the meter, and then it calculates the actual resistance. Now, between the leads, depending on what you have in there, and piece of copper wire, anything conductive, can be aluminum, it could be some sort of metal material, stainless steel. All this conducts current flow. So once you have the current flow, you can measure the resistance. The longer the piece of material in between the positive lead and the negative lead, or the red and black lead, the more resistance you have. In this particular diagram here, if you're watching it on YouTube or a podcast, you can see that we have a 0.3 ohm across there. So there is a very short piece of copper. So the short trace, short amount of resistance. So the resistance value is only 0.3. So two wire, the actual resistance of the device could be only 0.2 or 2 ohms. So let's say we're measuring a resistor of 2 ohms and we're reading on the meter 2.3. Why is that? Well, we still have the copper wire in the red probe and the copper wire in the black probe. That's a type of lead resistance. So that lead resistance is always there. So the red probe maybe is 0.15 and the black probe is probably 0.152. You add it together and you end up with 0.3 ohms. So that's why a 2 ohm resistor that is known to be good at 2 ohms would read 2.3 because of what we call lead resistance. This happens in all electrical measurements. I know that some manufacturers have different ways of dealing with it. We do a calibration, and for example, on our machines, we do a calibration down to the probe tip itself, and then we save these values, and these values are accounted for in every resistance measurement that is in the lower range. Now, Todd, let's talk about what happens with four wire. As Todd mentioned before, we know that with four wires, it makes the lead resistance redundant. So what's important here is that when you have a red lead and a black lead, you still have it, but you have two reds and two blacks going across your device. Now what happens here is when the two red leads touch the copper material very close to one another, not within a few microns, or depending on what kind of probe setup you have. If you're doing it manually, the manual probes, maybe you have 10 thou, 15 thou in between. But when you're using automatic testers, they're within microns apart, the probe tips. So you're basically touching the device that you're wanting to measure at the same spot within, let's say, 20 or 30 microns. There's the lead resistance is neglected in this case. So it's automatically reduced to zero. So you're going to get the true value of the component. This happens both on the red side or the positive side, the black side, the negative side of the reading. So if you truly have a 1 ohm resistor and you know that's good and it's come from manufacturer plus or minus 0.1%, so you know for sure that this resistor is 1 ohm. So you put the 4-wire Kelvin on there, you're for sure going to read 1 ohms because of the way that the calculation works, as Todd mentioned earlier today, that it reduces the lead resistance to 0, makes it neglect. So you get very, very accurate, very, very fine measurements. Now, 4-wire Kelvin works best below 1 ohm, but also works at any level of resistance.
Well, thank you, Rick. That's a great analogy of how the 2-wire and the 4-wire work. And one of the things about the 2-wire versus the 4-wire with the higher resolution, when we're talking changes in resistance, when Rick talked about the 4-wire measurement of 1 ohm, if there was a difference of 10% where you're talking just basically 0.1 ohm or 100 milliohms, sometimes those 2-wire measurements there are not going to be, you could have a very high resolution fluke meter or some other type of meter that has, what's supposed to be high resolution, but you're not going to get those milli and micro ohm differences showing up on the screen of the meter when you're looking at 2-wire. That's when we're talking about shunting out that extra lead resistance so that we can get the true measurement. That's some great stuff.
Yeah, Todd, you remember?
Go ahead.
You remember back when we started doing 4-wire Kelvin measurement, or we started getting requests for lower than 1 ohm? Our team was always coming back to us. The customer wants to test this job at 2 ohms, for example, and then we were getting out of tolerance because they were plus or minus 5%, and you're reading 2.3 ohms. So that was at a tolerance. So it took us a while even to train our team to put the 4-wire Kelvin on and turn on the option and do 4-wire Kelvin. So things really do change rapidly in this industry, and they do take time to change. But I'll let you continue, Todd.
Yeah, I mean that makes perfect sense. I mean, when you're talking just a standard copper resistive on a standard trace, we're looking at about 0.8 or so ohms per inch, or 0.9 ohms, half an ohm per 0.9 inches or so. And so when you have changes in the trace width and length, you got more copper. And so those numbers change, even though they're within spec, but having a standard measurement system running it on the probers and stuff, sometimes you can't keep that resolution. And when you're only talking 10% or 5%, an ohm is way too much movement. So you need to get down in there into this high resolution. Thanks for bringing that up, Rick. It was a challenge for us. So with that, when we're doing 4-wire Kelvin testing today, primarily a lot of it started out, we're doing barrel testing to look at plating quality. And so what I'm showing here today is a little bit of what these hidden defects that we're looking for when you talk about a plated hole or via feed through, goes by many terms. You're looking for uniform copper throughout the barrel. That way you can move the signal from one layer to another on a multi-layer, or from side to side on a double-sided. And if copper starts to deteriorate, or there was a problem during the plating and entrapment of air, you might get what we call thin copper or taper plating copper. Even though there might be a connection there during electrical test at the standard parameters, we would be able to detect that the barrel exhibited a higher resistive value against a known value or a standard barrel. And that's the kind of things that we're looking through on this slide and also on the next, where we're looking at defects where you can actually see what type of things this Kelvin high resolution test will pick up. You can see in this slide here where we have some very thin copper in the barrel, but we see here that this could make an electrical connection. And remember, with ET, we're using, of course, the theory of Ohm's law when we're setting our voltage current looking for resistance. But we're not sending high current. We have shunting circuitry in there so that we can detect current that's trying to run away or something. So in a standard electrical test, we don't have the, let's say, quote unquote, power to actually blow something up in a scenario like this. We might stress it a little bit, but we will see a connection through there. And if we have, less than, let's say it's a class 2 or type, class 2 or level B, we're looking at about 20 ohms of continuity. That might pass. And then when, it goes on and has goes through some thermal cycling, maybe, when it goes through assembly and it expands and contracts a little bit, and they do their power up test, which may be more aggressive, these could snap like a fuse, and that causes a latent defect in the field. And unfortunately, it comes back as something that is going to cost the manufacturer and maybe even the service center some money, depending on how the root cause analysis is done. But that's what we're looking for. And we also, like Rick mentioned too, we're not just looking at holes nowadays. We actually are looking at traces and circuits with the high-speed timing requirements of today. So that's where Kelvin is really taking off. So with that, I'm going to move into a little bit of the technical aspects. I'll let Rick talk about basically how a Kelvin test is set up. We have a couple of different ways that it can be done. So I'll let Rick take it away there.
Thank you, Todd. So most of the time we're doing a setup, we do not know the actual resistance of the traces or holes, depending what we're measuring, because it depends on basically the biggest question mark is the plating. Now the plating may vary, and the build actual of the copper thickness and the PCB board itself may change. So a lot of times, dominantly right now, we're doing probably a master learn on a bunch of pieces. 95% of the time, the other 5% of the time, we have we receive the values from the designer and we use them. So let's talk about the 95% of the time. So 95% of the time, we don't know the values, so we got to go out and find them. So we have a PCB board that's passed electrical test, the standard electrical test. Now we want to try and go a little deeper and see what's in there. So we take a batch of boards, and depending on what they really want, how accurate they want to be. Sometimes we're taking 10 boards, sometimes there's even up to 50 boards that we may take as the batch size. So we go ahead, we put it on the machine and we run it. And what we do when we're doing this test is when we're putting the probes on there in our software, it's adjustable, but we go up to 5 readings. So we take 5 readings on that pad the first time during our master generations, just to make sure that we're getting everything accurate. There's no poor contact or anything like that. So we're taking 5 readings, we're going to the next one, we're taking another 5 readings, the next set of measurements, the next set of measurements, 5 readings. And when the first board's done, we say, okay, we go to the next board. So then we do the next board. We take the readings of the next board and continue this process on until we get to the batch size that is agreed upon with the client about what we want for the master generation. When we have that, now we're going to take, now we've been doing mostly averages. We've looked at the data, and also there's a way to look at the data and throw out some boards that are not good. They use a bunch of batch, because it really depends on the plating cycle itself and where the plating is and how well the client's plating system is running. So if you have a defective plating, you may want to throw out some batches in the master, some boards in the master. So you have that option. If you want to keep everything in, you just basically take an average of everything and create that as a master. And then when your master is done, then you go on and you can retest the master boards over again if you wish. Continue on with the batch and test the batch as is, just like a standard netlist test then. So what the software does is for each reading or each pair, so you basically, if you break it all down, there's multiple probes on the machine at once. So you break it down, you need 2 probes, 2 sets of probes. Each probe tip has 2 wires or 4 wires going to it. So it's 2 wires, one on the probe tip on the bottom or left and right, top and bottom or left and right. And so you have 2 probes on each head, and you need two heads to be testing at the same time in order to make good connection and evaluate for your 4-wire Kelvin. So on a very slow pace, that's what happens. When you speed it all up, it goes in milliseconds. It's hard to see the test actually running. But once you get your master, it's going to compare the values for each one of those nets, each one of those pairs, and within the tolerances that you set. Now the tolerances A lot of people do the lower tolerance at a specific value and the upper tolerance at a higher value or lower value. And then they continue on testing the order until it gets out to the reporting, I believe.
Yeah, one thing to mention here, when we're looking at this screen here where we talk about our tolerance upper and lower, some people, you might be thinking, Todd and Rick, well, what does it matter on the lower tolerance? I mean, if you have zero resistance between the 2 points, isn't that totally acceptable? And I would say, in most cases, you're absolutely right. That tolerance really has not a significant effect overall. When you're looking for, we need to have a certain resistive value, upper tolerance allowed. But you have to remember, there's some really finicky, sneaky designers out there that have got a circuit designed to the point where it is so finitely tuned that if you actually did have too less of a resistive value, you might be allowing too much current flow to some high-tech device that may not even exist yet. But that's why the lower tolerance is still in there. For the most cases, yeah, you're right. It doesn't mean a lot, but there can be. So when we design it so the future allows us to have a window. If they want a window in there, then we can do that. Thank you very much, Rick. So moving on. So when Rick was talking about the learn, compare, or learn master generation. Once we have that created, we can go and we can look at it. Most of the equipment out there, including ours, has the ability to go in and look at what the machine read and what your master values are. And this is an editor screen here you can see where we show the, we give it a record name for each of the measurements, the values, upper and lower tolerance. And here, if you have administrative access to this, and you know that you've been testing and you see, okay, maybe that master had a value somewhere that, wasn't quite right. Like I say, this is not line level or operator level type stuff here. You need to have a supervisor authority or so, maybe even a customer authority to be able to do this. But you can go in and you can make a change. Say you were reading 3.2 milliohms, and the board actually was, as you found through the testing process, you're actually better than that. You're down to 1.5, 1.6 milliohm, and you can go in here and make the adjustment without having to go and do the whole learn master creation again. And also, if you were able to supply the values up front once they're loaded in, any minor tweaking or changing of the upper and lower tolerances can all be done here. And that's the editing part of it. I'll let Rick talk a little bit about reporting, of how once we get all this done and some of these engineers want to know everything about the board, this is where we go.
Yeah, so the reporting, there's a couple different ways of going about the reporting. We can just give a pass or a fail as the operators are seeing the board running on the machine. If any nets or any pairs fail, of course, out of tolerance, upper or lower, the machine will spit out that XY coordinate and label whatever's there on the data and tell you the reading and how far out of whack it was and etc. If it passes, it passes. It's within tolerance. So depending on what the engineers want, we can just give them a certificate that says certificate of compliance, say they were within this range, and list all the ranges. And if they want a detailed report, for example, Todd, I was working with a customer that was after repeatability last couple weeks. They were looking to test some boards and make sure the same board at different days was within plus or minus 2% repeatability. So we were going back and forth and doing some testing for that. It took a few weeks to go over and get the testing done, but everything came within 2%. So he was getting detailed. So detailed. So every measurement we do for 4-wire Kelvin, you give the location, you give the label, you give the read value, the expected value, the minimum value, and the maximum value. And okay, we put some more information in there, like the cycle information. Most likely at this level of test, you're going to put some serial number in there. So either the machine will scan the serial number, or The operators type in the serial number before the test, so it's all linked together. And then if you have a batch of 10 boards, for example, you output the batch. You can output one particular cycle, or you can output everything in one. You get it in a nice little handy dandy CSV file or Excel file, depending on what you want, or PDF. And then you can go do whatever you wish with that report. So that's line item by line item, the labels that are there, what's read, what the expected value was, what the lower tolerance is, what the minimum tolerance is. It's all there. All the information's there. So most people will take this CSV file and read into some sort of database and do some comparison. Like I mentioned earlier, this one particular engineer was doing comparison on different days, the same piece, to make sure the repeatability was there, and it worked out quite well. But so it's very adjustable, very easy, the interface that we have in our software to output this, or just keep it as a pass or a fail.
All right, great info on the reporting. I mean, I know when, this reporting is, we do it for 4-wire, we do it for inductance, and we do it for buried passives. And I know, some engineers in the development process, they like to make their scatter charts and their bell curves and all that, especially years ago when this buried passive stuff started, when we were still dealing with not so much on the omega-applied buried, but we were actually doing some carbon screening and things like that. Repeatability was really huge, and the reporting was definitely required to see where they were on their manufacturing process. That kind of wraps up where we were or where we wanted to be today on the whole 4-wire Kelvin. Some of the takeaways that we have today is the main thing we're looking for is plating anomaly, or when plating anomalies are suspected, and that can be both the plated through holes or surface traces or internal traces. Kelvin can be used to detect those types of things. We also learned that we can do this by a learned comparison type test, which Rick explained in the beginning for our 95+%, or we can be pre-programmed where the calculations have been done, so we know what to expect. We see that starting to grow a little bit. When you have a machine, a lot of times when you want to get into the higher resolution 4-wire Kelvin, when you negotiate the price of the machine or the options on the machine, a lot of times this is an upgrade type thing or an option, so it requires a little bit of extra hardware and maybe some software upgrades to it. So a lot of times you don't see these on the entry level machine, but with us, it's available. Basically used for extremely, high resolution measurements. We're not talking the 1 ohm, the 3 ohm, the 5 ohm, standard ET stuff. We're down in the milliohms and sometimes even down into micro with the measurement systems that are available. Like I say, milliohms versus ohm. When we're doing side to side or barrel test, we didn't really bring this up, but I know Rick said we want to be real close on the probes. But also when we're doing a barrel test, we want to be side to side, and we want to be as close as we can to the barrel annular rings if possible, because that provides the highest amount of accuracy. But, this always isn't the case. If you have via cap or via plug, sometimes you can't actually access that pad or that annular ring. So you need to sneak out down the network to the next available. Sometimes it can have a minor effect on some of the accuracy there, but this is high resolution stuff. And when you review the reports and the master, you can make some adjustments. Like I say, that kind of goes along with my last point there, where the more copper you have between the measurements, the higher that value is going to be, and you can have a possibility of a little loss of accuracy. You want to be as close as you can from your force and sense probes to make sure you can get as accurate as you can. Those are my points. If Rick has some closing comments on today's podcast, welcome those.
So Todd, why do we do 4-wire Kelvin measurement?
Why? Well, 4-wire Kelvin is designed by, like I said, Mr. Thompson. We do that to mostly, a lot of times what a customer will do to statistically analyze plating, or if there's a suspect. A lot of times what may happen is if a board fails at ET and a cross-section is done and they find that there may be taper plate or some plating anomaly, that referee then could cause a 100% retest, because what we don't want to see is anomalies in the field post-manufacturing going out to the customer where it worked fine and passed test, went out to assembly, it was fine, and it gets out in the field, and 3 months down the road, all of a sudden it fails. And this is extremely important when we're talking about medical reliability, equipment, and aerospace, and military. So that's why we're doing these high resolution tests to look for these anomalies that can't necessarily always be detected at your standard electrical test.
That's right. People want reliable circuit boards, Todd. Exactly right. The underlying problem usually is something to do with plating or the plating process itself. So you're checking the reliability of that. But as a buyer of a PCB board, if you have a medical board, we see it in communication, we see it in automotive as well. If you want it to be 100% reliable, then you should be adding in the 4-wire Kelvin testing to it, so you know that the copper in those holes and the traces is within your desired specifications. So you're not going to pop it, you're not going to go over current, you're not going to have any problems with that circuit board later on down the road.
Absolutely, and as we talked about earlier, as we advance in technology, which we are leaps and bounds year to year, this type of test and tuned circuits and current flow measurements and changes in resistive value. Because remember, as I talked in the beginning, Ohm's law, voltage equals current times resistance. You can't get away from that law. It's gonna be there. If you have a set voltage that's constant, you tweak around with voltage or tweak around with resistance, you're going to adjust the current no matter what. You can't get away from that. So if you have differences in that plating value causing resistive value changes, you're going to ramp up or ramp down current based on these minor changes. And as things get, smaller and smaller and smaller, what didn't used to be a problem with current flow can be a major problem nowadays when we're talking very intricate and parts that can be damaged very easy, just like in the back CMOS days when static electricity was the #1 killer at CMOS. But I thank you all for joining us today. On behalf of Rick, Moran, and myself, we're glad you came by to learn about 4-wire Kelvin testing. And if you have any questions, you can drop us a line, send an email to info@gardien.com. That's info@gardien.com. Or you can find us on your favorite podcast website, Buzzsprout, YouTube, and you can find it on our website at www.gardien.com. That's www.gardien.com. With that, we'll see you next time on the Gardien Podcast Series.